I'm having some problems recording this video, so I'm having to do the first part over. At the top of the page on test 1, you see a table of Fibonacci and Lucas numbers. I give you the first 18 of each, and in question 1 I ask you to compute the 19th and 20th Fibonacci and Lucas numbers. And you know by adding the 17th and 18th, we get the 19th Fibonacci, 4,181. Then adding the 19th and the 18th, we get the 20th Fibonacci, 6,765. And same for the Lucas numbers, we do the same. We get the 19th Lucas, 5,778, and the 20th Lucas, 9,349. All of you can go back to your own version of test 1 and see that table at the top where I give you those numbers. I will also give you any Fibonacci Lucas numbers on the final. You'll have a table provided. Number 2, to show that you can read sequence notation, evaluate this mathematical expression. 2L5 plus F7 plus 1. In other words, 2 times the 5th Lucas number plus the 7th Fibonacci number plus 1. Well, the 5th Lucas number is 7, so it's 2 times 7 plus the 7th Fibonacci is 13 plus 1 is 28. So now number 3, problem number 3, we want to write and evaluate the expression f sub n minus 1 plus f sub n plus 1 using n is 2, 3, 4, and 5. So we want to compute 5 examples of this expression. The n minus first Fibonacci plus the n plus first Fibonacci, where, first of all, n equals 2. So I'm going to write n equals 2, and move over a little bit, put n equals 3, n equals 4, and giving myself some room to compute here, n equals 5. If n is 2, I am computing f1 plus f3, which is 1 plus 2, which is 3. Use your table given. When n is 3, I'm computing f2 plus f4. And the second Fibonacci is 1, the third Fibonacci is 3, the fourth, so it's 1 plus 3, or 4. When n is 4, I want the third Fibonacci plus the fifth Fibonacci, and that is 2 plus 5. Using your table, adding, we get 7. And when n is 5, we are computing f4 plus f6. Looking at your table, you get 3 plus the 6th Fibonacci is 8. Adding, we get 11. Now that's full credit there if you get these answers. But remember, we're looking for a pattern. If you look at part B, you'll see we're going to ask for a pattern. So let's find that pattern now. When n was 2, I got 3. When n was 3, I got 4. When n was 4, we got 7. When n was 5, we got 11. And those are Lucas numbers. So let's ask which Lucas numbers. Well, 3 is the third Lucas number, so I'm going to put L3. When n was 3, I got 4, which is the fourth Lucas number. When n was 4, I got 7, which is the fifth Lucas number. I'll write L5. And when n was 5, I got 11, which is the sixth Lucas number. So we do see a pattern here. And we'll go on to the next part of the question, and we can write what that pattern is. That we found in part A, calculate the value of f sub n minus 1 plus f sub n plus 1 when n is 18. Well, if you look back at that pattern, when n was 2, we got L3. When n was 3, we got L4. When n was 4, we got the 5th Lucas. And when n was 5, we got the 6th. So here, n is 18. Surely we are going to get L, the 19th Lucas number. And the 19th Lucas number we calculated, and it is 5778. So this shows me, if there's a question like this on the test, that you were able to find and extend a pattern. Now, in part C, you want to say this in a general way. From the pattern you found in part A and verified in part B, complete a general formula for f sub n minus 1 plus f sub n plus 1. Okay, that's for n in general. Well, if for n in general, you know that we're going to get the n plus first Lucas number. So this is just L sub n plus 1. And you will not get full credit on something like this if you write the subscript in a sloppy way. For example, I'm going to show you some ways that students write this. Like if they write the L, let me do it in a different color here. I don't want you to think this is right. L sub n plus 1, something like that. That's not right. I want L, and then the subscript tells me which one we are looking for. It is not the same thing as L sub n plus 1. They are not equal. This is what you want. The 1 is added inside the subscript. Problem 4. Here is a different sequence. Let's call it T sub n. 2, 0, 2, 2, 4, 6, 10, 16, 26, 42, 68, and so on. And the last few numbers, it goes out, oh gosh, probably they're not, I don't know, but looks like there's about maybe 22, 23 terms of the sequence given. But it's a Fibonacci type of sequence. It just starts with 2, 0 instead of 1, 1. So you could generate the first 20 terms yourself by just adding the 2 before it to get the next one. Part A, describe either with a good sentence, and by that I mean a sentence with a period, a noun, a verb, etc., an English sentence, which is much harder, I think, than just giving a formula. Describe either with a good sentence or with a formula how the terms of this sequence are generated. One thing I hope you got in this class is that it is hard to write about mathematics if you don't have notation, mathematical notation. The notation is to give us an easy way to say things. So in notation, let's see, this sequence is called T sub n. So you could write T sub n plus 1 is equal to, and now the 2 before it would be T sub n, and the 1 before that, T sub n minus 1. So that's usually the way I write it. I think of n plus 1 as T sub n plus 1 as the next, the one coming after T sub n in general. So T sub n plus 1 is equal to T sub n plus T sub n minus 1. And I should say where n begins. N must start at 2 in this case. 2, 3, 4, dot, dot, dot. N equals 2, 3, 4, and so on. Now you could also write a sentence. I'll just say it. Each term of the sequence T sub n is found by adding the 2 terms before it, period. B, part B. Do just one calculation that will indicate that as n gets larger, the same thing will happen in the sequence of ratios as it did in the sequence of ratios of Fibonacci numbers. I should have, after the sequence of ratios there, I should have had of Fibonacci numbers. Oh, somehow that didn't come out on the video. On your test it says happen in the sequence. Do just one calculation that will indicate that as n gets larger, the same thing will happen in the sequence of ratios as did in the sequence of ratios, and it said f sub n plus 1 over f sub n. I don't know why that didn't translate into the file. Okay, so let's talk about this for a minute, and then we will do one calculation. Well, what did happen in the sequence of ratios? In the Fibonacci sequence, if you go out far enough, 15, 16 terms, and you divide a term by the one before it with your calculator, like maybe you just take f sub 20 and divide by f sub 19, you're going to get a number that is very close to phi, 1 plus the square root of 5 over 2, 1.618. And that happens if you look at problems 8 and 10 in section 2.2. They were on our problem set for the Fibonacci numbers. We went through this very carefully. Any sequence that is generated in that way has its sequence of ratios tend toward phi. We could say f sub n plus 1 over f sub n arrow phi. That's what's happening. And to verify that it's happening in this sequence, let's just take the last two numbers that I gave you in the sequence. The last two, I don't know if it's if it's t20 over t19. That's not important. I'm just going to take the last two. The last term of the sequence I gave you in the problem was 8,362, and the second to last term, the one before it, was 5,168. So I wrote the fraction 8362 over 5168, and I'm going to plug that into my calculator, and what do you know? I get 1.61803, and that is approximately, squiggly lines instead of an equal sign, phi. So the answer to this question partial credit would be given if you just took the ratio and you said 1.618034. But to show that the same thing is happening that happened in the Fibonacci sequence, you have to tell me that that number is close to phi. Problem number 5 is really just you either know how to do it or you don't, and you most likely will have a question like this on the final. So just look at the process. How do you do it? Express the natural number 1935 as a sum of non-adjacent Fibonacci numbers. And in part B, we asked to express that number as a product of prime numbers. In other words, it could have been said prime factor 1935. So let's do part A. We want to write this number 1935 as a sum of Fibonacci's. And we want non-adjacent, not next to each other. So there's a certain way that you do it. Okay, I write down 1935 equals, and I go to my list of Fibonacci numbers, and I take out the biggest Fibonacci I can. The biggest Fibonacci less than or equal to 1935 is 1597. So I write 1597. Now I subtract 1957 there, and I have left 338. So in other words, I'm saying that 1935 equals 1597 plus 338. Now, if 338 was a Fibonacci number, I'd be done. But it isn't. So I am going to rewrite this expression, 1597 plus, and from 338, I will take out the biggest Fibonacci I can, and that is 233. So I write 1597 plus 233 plus 105. I just took 338 and wrote it as 233 plus 105. Okay, well, if 105 were a Fibonacci, I'd be done, but it's not. So I will rewrite 1597 plus 233, but now the 105, I'm going to take out the biggest Fibonacci I can, and that is 89. 105, if I subtract 89, I get 16. So now I have 1597 plus 233 plus 89 plus 16. Well, do the same thing. 16 is not yet a Fibonacci. I take out the biggest I can. Every time, that's the key. Take out the biggest you can. And this time we will be done. 1597 plus 233 plus 89. And now in my last step, I write 13 plus 3. 3 is a Fibonacci, so I stop. So that is the answer. 1935 equals 1597 plus 233 plus 89 plus 13 plus 3. Many of you, when you did this problem, you did write it as a sum of Fibonacci's, but you didn't write it, some of them were adjacent. For example, if at the end you changed 3 into 2 plus 1, then all of the Fibonacci's you wrote were not adjacent, and you would lose a little bit of credit. That word non-adjacent is important. Okay, so now in part B, we want to prime factor that same number, 1935. So everybody did really good on this one. 1935. I think you're used to making little trees. Divide, it's not divisible by 2. Let's see, is it divisible by 3? Well, let's see, let's add the digits. We get 1 plus 9 is 10, 18. Yes, 18 is divisible by 3, so the number will be divided by your calculator, and you will get, 3 times 645, no, 3 times 645. 645 still has sum of digits divisible by 3, so that is divisible by 3 again, and we get 3 times 2, 1, 5, and 215 is no longer divisible by 3, but it is divisible by 5, so let's say 5 times, and 5 goes in, 4, 43. Oh, 43 is a prime. So we're done. And we now write 1935. You have to write it out. I will not accept the tree as full credit. It says write it as a product of primes. So you had 2 factors of 3. Go back and see what primes you got here. 3, 3, 5, and 43. So to write it as a product of primes, we'll write 3 squared times 5 times 43. You have to express the answer as a product of primes. Problem 6 is a pigeonhole principle problem. Explain why if you pick 5 different natural numbers from 1 to 8, there will be at least 2 that add up to 9. You can see by the statement of the question that this is a pigeonhole question. And I give you a hint. I say consider the possible pairs that add up to 9. Well, let's do that first then. That's the hint. So let's write down the pairs that add up to 9. 1 and 8. 1 plus 8 equals 9. Or 2 plus 7 is equal to 9. Or let's see, 3 plus 6 is 9. Or 4 plus 5 is 9. Now, 5 plus 4 is the same thing. We're looking at pairs of numbers. So in other words, we're looking at the pair 1 and 8, the pair 2, 7, the pair 3, 6, and the pair 4, 5. Those are the only pairs that would add up to 9. And you're going to pick 5 natural numbers. So the best way to write this out is 5 is greater than 4. And since we are choosing 5 numbers, at least 2 will be from the same pair. Those two will add up to 9. And you should say what you used, the pigeonhole principle. If you use the pigeonhole principle, say that you did. That adds to the quality of your answer. Since we are choosing 5 numbers and there are only 4 pairs, that would be another way. I wrote the inequality 5 greater than 4, but really an even nicer way to say this would be, since we are choosing 5 numbers from 4 pairs, at least 2 will be from the same pair. That's the pigeonhole principle. Those 2 will add up to 9. I put in this pigeonhole principle problem too. I thought you might need 2 examples. Problem 7. This was not on your test. Suppose you throw 200 darts at a 1 foot by 1 foot square dartboard, and all of them stick. Use the pigeonhole principle, or possibly I wouldn't say use, I might just say explain why at least 2 of the darts will be less than 2 inches apart. Well, that's really hard to think about, but you know that you're thinking of pigeonhole principle, and it's 1 foot by 1 foot square, so a good way to start would be to draw a picture and see. I'm going to draw a 1 foot by 1 foot square here on the paper. And I know that a square is 12 inches, so, you know, I'm going to divide this thing up into square inches. So let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is really a bad square. 11. So there, I'm going to have to go down further. I'm just making a square. You wouldn't need to do all of this, but I'm dividing it into square inches. And so then I'd put 12 lines this way. And, you know, let's just sketch this, okay? So we have how many square inches? A 1 foot by 1 foot is a 12-inch by 12-inch board. And so that means that there are 144 square inches. So we're throwing 200 darts at 144 square inches. By the pigeonhole principle, at least 2 darts will land in the same square inch. I'll say that again. We are throwing 200 darts at a 144 square inch board. By the pigeonhole principle, since 200 is greater than 144, at least 2 darts will land in the same 1 square inch. Okay, so if you think about a square inch here, the longest distance in a square inch would be that distance right there. Well, it's a 1 by 1. That distance is the square root of 2. The diagonal of a 1 by 1 inch square is the square root of 2, which is certainly less than 2. So there's no way you could put 2 dots. There's no way you could put 2 dots in a 1-inch square that were further than 2 inches apart. So your answer could be, you are throwing 200 darts at a 144 square inch board. By the pigeonhole principle, at least 2 darts would land in the same 1-inch square. And therefore, those 2 darts would be less than 2 inches apart. Question 8 is about the prime numbers. Here are the first few prime numbers, and I give you a list up to 53 and ... Define a prime number. Okay, you just write the definition. A prime number is a natural number greater than 1 that is only, or no, let's say that is divisible by only 1 and itself. Again, there's partial credit that could be given for a definition, but full credit will only be given if it is a full sentence and all of the important words are there. Here the important words is prime, that's what you're defining, natural number, greater than 1, divisible by only 1 and itself. Is 887 a prime number? Well, we can't be sure by just looking at it, but we'll try a few prime. Let's just try a few. Is it divisible by 3? Well, the sum of its digits is not divisible by 3, or you could just try 3 with your calculator. By the way, clearly it's not divisible by 2. It's not even. It's not divisible by 3. Try 5. Well, you can see it's not divisible by 5. Try 7 into 887, and you'll see it's not divisible by 7. And you know, how far do we need to keep going? Remember, we want to justify our answer. So I'm going to take the square root just to see ahead so I don't keep going further than I have to. The square root of 887 is about 29.7. So I know that if I try all prime numbers less than or equal to that square root, and none of them divide evenly, then I'm done. I'll know that 887 is a prime. So I've got to try the primes up to and including 29. And I do so. I try 11, nope, 13, nope, 17, 19, 23, and 29. And notice I showed on my paper here that I did try those. Or you could write a sentence. I tried all prime numbers up to 29, which is the largest prime less than or equal to the square root. And none of them went in, so I can say yes. And just showing me the primes that you tried and that you took the square root, I can see that you're justifying it by the fact that the square root is 29.7, and you tried all primes up to that. Question 9. Consider the following sequence of numbers: 21, 201, 2001, 20,001, 200,001, ... In other words, each number begins with 2 and ends with 1 as its right-hand digit, and every time we just put it one more zero in between. That's a sequence of numbers. How do you know immediately that none of these numbers are prime? Well, the sum of every one of those numbers, the sum of the digits is 3. So the sum of their digits is 3. So every number in the sequence is divisible by 3, and hence not prime. If you know what you're talking about, then you will just naturally write this out in good sentences. Question 10. We used a proof by contradiction to prove that there is no biggest prime. What does this mean about the set of prime numbers? Well, first of all, if there is no biggest prime, it would mean that the set of prime numbers is infinite. So let me write that in a couple different ways and kind of tie it in with something on the second exam. The set of prime numbers is infinite. And just look, we could list the set of prime numbers, right? I did it for you before on the last couple slides. In other words, 2, 3, 5, 7, 11, 13, is an infinite set. That's what we proved, that it is infinite set. Well, it's also listable, isn't it? We just did it. 2, 3, 5, the first, the second, the third, the fourth, the fifth. And so what is the cardinality of the set of prime numbers? Let's just write that down. Since we can list this infinite set, the cardinality of the set of prime numbers is equal to the cardinality of the listing set. Remember, the natural numbers. Any infinite set that can be listed has the same cardinality as n. But what we had to prove in here was that there were infinitely many. And so I would like to go over just an outline of that proof. You're not going to be asked to prove that there are infinitely many primes, but proof by contradiction will come into the test. So let's go through the outline of what we did to prove that there was no biggest prime, and hence that there are infinitely many. So here's an outline of a proof by contradiction. Prove there is no biggest prime. Okay, so suppose not. Suppose there is. Suppose there is a biggest. Call it P. big P. So that's a biggest prime P. Now, we learned in that section that if we form a number in this way, I'll say let or make capital M be equal to 1 times 2 times 3 times all the way up to ... times P, and I add 1 to that huge sum, that M is not divisible by 1, 2, well, not 1. M is not divisible by 2, 3, 4, 5, 6, 7, and all the way up to and including capital P. If you divide M, which is the product of P and everything less than P, and then add 1, if you divide that number by any of the numbers up to and including P, they will leave a remainder of 1. So if we let M be that number, this was the trick, then M is not divisible by, okay, so M is not divisible by 2, 3, 4, all the way up to P. Well, therefore, it is not divisible by any prime, because we said P was the biggest prime. So all of the other ones are less than P, and we can say, therefore, M is not divisible by any prime number. Based on our assumption that there is a biggest, we were able to create a number that is not divisible by any prime then. Well, if this number M is not divisible by any prime number, then M must be prime, the number we made. Must be prime itself. But M is a whole lot bigger than P. So our assumption that there is a biggest prime is incorrect, is false. Therefore, you can say there is no biggest prime, which means that the set of prime numbers is infinite. Remember the structure of a proof by contradiction. Whatever you're asked to prove, just suppose it's not true and proceed in a logical fashion from that assumption until you get to something you either contradict, a theorem, or you get to a fact that you know is not true.